Bismillahirrahmanirrahim. Today we are going to study the equivalent circuit of induction motor. An induction motor is called a singly excited machine, whereas the synchronous motor is called the double excited machine, because in the induction motor the power is also only supplied to the stator circuit, but whereas in the synchronous motor the field current is also supplied to the field circuit which is present on the rotor. That's why the synchronous motor is called double excited machine. Now moving towards the equivalent circuit of an induction motor, as we all know that the induction motor operates on the basic principle of induction, and transformer also operates on the basic principle of induction, and this is the basically reason that we are going to study the induction motor right after the transformer, and that's why their equivalent circle also resembles with each other. Thus the induction motor model will be developed by starting with the transformer model. First we consider the transformer model, and then we decide how to take the rotor frequency and other similar induction motor effects into the account, and then a little bit modify this transformer model which will become the induction model. The transformer model of an induction motor. First, a transformer equivalent circuit which is representing the induction motor model is also shown in figure, and I am also going to draw it here like that. This is the resistance, this is the reactance, co-resistance, magnetization reactance, winding, rotor winding, rotor resistance, rotor reactance, and short circuit. This is rotor voltage, this is the stator voltage. I2, this is rotor current, and this is the effective turns ratio. This is R1. In transformer model, this is the primary resistance and primary reactance, whereas in the induction motor model this is the stator resistance and stator winding reactance. This is the core resistance, this is the magnetization reactance, which is the same as in transformer as in induction. This is the rotor winding resistance, and this is the rotor winding reactance, and which is short circuit. As we study in the previous lecture that I told you that all the squirrel cage, the bars are also short circuit, and the wound rotor motor, the winding is also short circuit. So that's how this induction motor model looks like. We will study deeply again. The value of Xm is very small because why its value is very small in the induction motor equivalent circuit as compared to the equivalent circuit of transformer. The reason is the air gap. As this is the air gap. If this is this winding, here is the secondary winding, and this is the air gap. Because of this air gap, the reluctance is very high, and reluctance is very high, so high amount of Im is required to generate same flux. When Im is required, so corresponding Xm is very small, so that's why Xm in the induction motor is very small. Same in transformer. When we draw the magnetization curve, which is between the magnetomotive force and flux, it looks like that, similar like that. But this is for transformer. But when we apply the same amount of magnetomotive force on the induction motor, the resultant flux produced is little bit less than in the transformer, and its slope is little bit shallower than to the transformer. This is because this is for induction motor, and less flux is produced by the same amount of magnetomotive force. Here flux value is high, here flux value is low. This is for induction motor and this is for transformer. At this amount of force, the flux produced in induction motor is this, but flux produced in the transformer is this. So that's the reason is the same air gap. In motor there is the air gap. When there is air gap, as we already studied in chapter number 1, the reluctance of air gap is very high. When the reluctance of air gap is very high, high amount of magnetization current is required to produce this kind of flux, and the flux produced with the same magnetomotive force is the small. So this is the reason, that's why its shape is like that, a little bit shallower. In transformer there is also the concept of in induction motor there is also the concept of turns ratio. Here same like in transformer. In transformer, as we already know, that the turns ratio is V1 V2 divided by N1 on 2. This is the primary winding, number of turns on the primary winding, and the number of turns of the secondary winding. Whereas the effective turns ratio AEFF in the induction motor is defined as the ratio of the conductors per phase on the stator to the conductors per phase on the rotor. But as we know, the wound rotor motor, the winding takes place on the rotor. So in a wound rotor motor, the effective turns ratio calculation is easy, whereas the cage rotor motor, the effective turns ratio calculation is little bit difficult. So after turns ratio, here ER, the voltage is induced on the rotor winding. Because of this voltage, current will flow through the rotor winding. Now there are some similarities and differences also present in the transformer equivalent circuit model and the induction motor equivalent circuit model. Similarities are this is similar, this is similar, this is similar, this is similar, this is similar. But the differences occur at the rotor voltage ER. This is, and this is, and this is. These will be different in the induction motor model, and we will study here that how these values are different in the induction motor model. Now we are going to study the rotor circuit model. In this model we will study how the rotor model parameters will behave and how it is different from the transformer secondary circuit. First of all, we will study that when the voltage is applied to the stator winding, a voltage is induced in the rotor winding. But this induced voltage is directly proportional to the relative motion between the rotor and the stator winding magnetic field. And here I am showing you, the greater the relative motion between the rotor and the stator magnetic field, the greater the resulting rotor voltage and rotor frequency. Means when the rotor is stationary, the relative motion is very large, so induced voltage and current is very large. When the rotor is moving with the synchronous speed or the moving with the same speed of the stator magnetic field, there is no relative motion, and when there is no relative motion, there will be no induced voltage and current. From this, when the relative motion is very high, slip is 1, and when relative motion is very small, slip is approximately 0. So we can call that the magnitude and frequency of the voltage induced in the rotor is directly proportional to the slip of the rotor, and the induced voltage and induced frequency can also be written as ER is equal to S of ER naught, and ER naught is the logged rotor induced voltage. And same will be go towards the frequency. FR can also be written as S of FE. S of FE is the system frequency and also the logged rotor induced frequency. Logged rotor induced frequency. So that's how the induced voltage on the rotor will behave. The rotor resistance, this is rotor resistance is constant. It is the independent of slip, whereas XR is not constant, it depends upon the slip. As XR is given as omega LR, and we know omega is equal to 2 pi f. For the rotor it is 2 pi f for LR, and f of R we know it is equal to S of FE. This is equal to 2 pi S of FE L of R, 2 pi FE L of R, which is equal to S of F of R naught, S of which is equal to S of X of R naught, and X naught is the this one is the locked rotor reactance. But a rotor which is moving with slip speed have this reactance. So when we are going to develop the rotor circuit model, it looks like this is the ER, generated voltage, ER, reactance and resistance. As studied that the resistance of rotor will be same, it will be constant. This is X of R and this is E of R. But when they are moving with some slip speed, this is equal to J of X of R naught and it is equal to S of E of R naught. So these two parameters will modified into this term while developing rotor circuit model. But in the transformer, if it was a transformer model, so there will be no concept of this and it will remains like that, J of XR and E of R. Here is the IR, and when we are going to calculate the rotor current, from this figure the rotor current is equal to, by Ohm's law, ER this one divided by this impedance, which is R of R plus J of X of R. As E of R is equal to S of E R naught and X of R is equal to S of X of R naught. Putting these values here, it is equal to S of E R naught divided by R of R plus J of X of R naught. This is IR. Dividing both equation by S divided by R by S plus JS X of R naught divided by S. This has this has this. Divide whole equation, this by S and this by S. It will become E of R naught divided by R of R divided by S plus J X of R naught. In this way, we can calculate IR by through ER naught. So as we know, the ER naught value calculation is easy because it is independent of the slip. So in this point of view, it is these calculations becomes more easy. So in this way, it is possible to treat all the rotor effects due to varying rotor speed supplied with the power from a constant voltage source ER naught. As we have a constant voltage source ER naught, so it is possible to use ER naught for all the calculations. So the equivalent rotor impedance from this point of view would be Z of R equivalence would be R of R by S plus J of X of R naught. And thus the rotor equivalent circuit using this modified convention should be look like that. In this, like here it is use E or naught constant, J of X or naught, and resistance is divided by slip. So these calculations will depend on E or naught, not E or naught multiplied with the sum slip. This is the constant voltage source. Now this graph is showing the rotor current as a function of rotor speed. In the beginning, when the rotor speed is 0, the relative motion between the rotor speed and the stator magnetic field is very high. E induced is very high. When E induced is very high, so current induced is very high. Similarly, when the speed of the rotor increasing, the induced voltage decreasing and induced current also decreasing, and when it reaches up to 100%, the induced voltage is 0 and the induced current will also be 0. So this is the graph of the E induced versus as a function of rotor speed. Now at the end we are going to drive the final equivalent circuit of an induction motor. To produce the final per phase equivalent circuit of an induction motor, it is necessary to refer the rotor part of the motor model over to the stator side. Same like as we did in the transformer, we referred the secondary side towards the primary side. In transformer, we already studied that we did VP Vs dash is equal to A of Vs. This is the secondary side referred towards the primary, and IP is equal to Is dash is equal to Is over A, and Zs dash is equal to A square Zs. We already studied this and we already derived these equations. Now in order to convert the rotor model, which is the secondary side of the transformer, which behave as a secondary side of the transformer towards the primary side, so these equations look like E rotor is equal to effective turns ratio into ER naught. I2 is equal to IR over A over effective turns ratio, and Z2 is equal to effective turns ratio square into R of R divided by S plus J of X of R naught. From here, if R2 is equal to A effective का square R of R, and X of 2 is equal to A effective का square X of R naught, Z2 is equal to R2 by S plus X2. So the final equivalent circuit referred towards the primary side or towards the stator side looks like like that. This is the R1, J of X1, I1. This is the applied voltage. Core resistance, magnetization reactance, magnetization current, I2. This is the reactance referred towards the primary side. This is the reactance referred towards the primary side, and voltage here is E1. So this is the final equivalent circuit of an induction motor, which look like approximately the same the equivalent circuit of a transformer referred towards the primary side. The only difference between the induction motor equivalent circuit and transformer equivalent circuit is this. In the transformer equivalent circuit, the value of here is R2 and it is independent of slip, but in the equivalent circuit of induction motor, the resistance value will depend on slip and its value will change. So this is the equivalent circuit of an induction motor. Okay, thanks.